Hey AP Chem, I am going over some questions from last week's practice exam today. I have to apologize. I have been extremely, well, I don't know if the right word is busy, but just bottled down with a lot of things to do at home. Not just like work stuff, but we actually put in a new sink in the kitchen yesterday and had some people help out with that, and it just took a long time yesterday and just been kind of busy with a lot of different things to do. With my daughter Audrey, she's 2.5, and she's very demanding of a lot of attention. Sometimes we have temper tantrums, and some cases that kind of derails the day. So I am doing the best I can to keep up with your questions. I'm going to do the multiple choice questions that you had problems with from last week on the test. I want to go over that today in this video. But overall, like I said in the last few messages to you guys, at this point, it's kind of up to you guys to really study. I can guide you and I can give you extra problems and questions and things like that, but you really need to be putting in some more time to study the material that you need to go over, whether that's kinetics or acids and bases or equilibrium, whatever that is. You need to focus on the topics that are struggles for you so that you are ready for that May 14th test, which is still happening. It's just going to be online now. Matthias asked me a few days ago what specific topics are going to be absent from the test this year, and it does seem to be that the topics of acids and bases and applications of thermodynamics will not be on the test this year. So pretty much anything involving acids and bases, you can pretty much assume that's not going to be on the test. Equilibrium will be, of course. I don't think that they would use anything involving Ka or Kb because that's an acid-base topic, but no matter what, I really feel like you should have a solid concept of those topics before you go on to college. So I'm going to continue giving those kinds of questions just because they're good. And if you are going on to chemistry in college, you will definitely have to know acids and bases chemistry. Applications of thermodynamics, those topics are primarily things about the Nernst equation and calculating delta G from the equilibrium of electrochemical cells and things like that. So the standards, just knowing delta G, delta H, and S, what those mean, and being able to calculate those from equations. I think that's going to be on the test, but the Nernst equation and delta G involving the electrochemical cells and stuff like that, I think that's going to be gone. I messaged you guys a few days ago specifically going over those two topics and then linking a PDF that has the exact step-by-steps, well, not step-by-steps, but the exact listing of what that means for units 8 and 9 being not in this year's test. Regardless, let's go over the test from 2014 and the multiple choice questions. Let's get into it. So I have a bunch of them here that I want to go over from that message board. So number 4 was the first question that people asked about. Excuse me. And this is looking at this reaction right here, barium oxide at equilibrium with barium BaO. So this is BaO2 at equilibrium with BaO and oxygen gas. It has an enthalpy of 162 kilojoules per mole of reaction. And it says a sealed rigid vessel contains BaO2 solid in equilibrium with BaO solid and oxygen gas, as represented by the equation above, which the following changes will increase the amount of BaO2 in the vessel. So this is a question that utilizes Le Chatelier's principle in order to answer it, but at the same time, it doesn't. So Le Chatelier's principle really hinges on the idea of increasing or decreasing the amount of substances at equilibrium to cause a disturbance in that equilibrium to adjust how much is produced or how much reactant is regenerated in the equilibrium. So the problem, though, is that you've got solids. You've got a solid on the reactant side and a solid on the product side. So at equilibrium, the only thing that matters actually is the concentration of oxygen gas. So really, we need to be looking, because the solids are there, Le Chatelier's principle doesn't really apply because you can't, those two things aren't in the equilibrium expression. So we're looking for an answer here that doesn't really have anything to do with the amount of stuff that's present and how that affects the quantities at equilibrium. Instead, we're going to be looking for something that isn't about quantities. And the only one that really works here is the D, lowering the temperature. they put in the enthalpy value there for a certain reason. Because the solids are not going to be affected by how much are there, well, enthalpy is still going to be a thing that makes, adding heat or taking away heat can produce one or the other. So because this reaction is endothermic, that means that heat goes in. It's a reactant, so to speak. So lowering the temperature means that we would lower the heat reactant. And so therefore, the reaction is going to shift to the left to produce more of the BaO2. And that's really, we're kind of using the theory behind Le Chatelier's principle, but it's really more of a thermodynamics idea here. Heat added in or heat taken away is going to move the reaction one way or the other. And so in this case, D is the correct answer. Number 5 is the next question people asked about. This one is, excuse me, a little stuffing in my eye here. It says, which of the following best helps to explain why the value of delta H for the dissolving of calcium fluoride in water is positive? So enthalpy being positive when something dissolves means that the temperature of the solution that we're holding is going to get colder. It's going to feel colder in our hands in order for this to dissolve. So heat has to go into this ionic compound in order to get it to dissolve. So why is the enthalpy positive? Well, CaF2 is insoluble in water. Doesn't make sense because they're saying it is soluble. B, CaF2 dissolves in water to form CaF2 aqueous particles. It's an ionic compound. That doesn't make any sense. It's going to dissolve into ions. And the correct answer is C. Let me go back to it though in a second. D says calcium 2+ ions have a very strong ion dipole interaction with water molecules in the solution. That answer doesn't really have anything to do with why enthalpy is very large or why it's positive. I'm not sure what they're trying to get at with that one. If that were a true statement, that would mean that calcium ions would want to come out of the ionic crystal of calcium fluoride. They would be drawn towards the water molecules because the Ca2+ would be pulled to the polar sides of the water, and that would be a favorable interaction. But because this reaction has an endothermic enthalpy, that means that it's not favorable for water to have that interaction. Instead, C makes the most sense. Calcium 2+ ions have very strong ion-ion interactions with F- ions in the crystal lattice. Basically what it's saying is the calcium and the fluorines are really, really strong, stuck together very well. And in order for us to break that ionic bond, we've got to add energy in. So in this case, C is the correct answer. You've got to add energy in to break that ionic compound bond. Next question is number 6. A lot of times these questions were kind of in a row. Some of them will be mathy, so I'll have something to show, but a lot of them are just questions about the theory here. And that's kind of what you'll expect on the test in May. Not a lot of math, but most of them are theory-based. Number 6, under which of the following conditions of temperature and pressure will H2 gas be expected to behave most like an ideal gas? This is really just remembering what an ideal gas, what conditions of temperature and pressure are most likely going to be with an ideal gas, and that's going to be where a gas exhibits the most gaseous-like properties. So at a pressure that's very, very low, that lets gas molecules expand and separate from each other really, really well, and temperatures that are very, very high, which will allow those gas particles to further separate from one another. When gas particles are highly condensed or at a very low temperature, they're more likely to condense into a liquid. So the best answer here is C, 500 Kelvin and 0.1 atmospheres. So ideal gases are low pressure, high temperature. That way they get away from each other really, really well. Number 7 was the next one people had questions about. It says the volume of a sample of air in a cylinder with a movable piston is 2 liters at a pressure of P1 as shown in the diagram above. The volume is increased to 5 liters as the temperature is held constant. The pressure of the air in the cylinder is now P2. What effect do the volume and pressure changes have on the average kinetic energy of the molecules in the sample? So basically, the molecules of gas in this 2 liter space here, are allowed to go into a 5 liter space because the plunger's lifted up. And they're asking, how's that going to affect the kinetic energy of the molecules? Remember, kinetic energy is equal to 3/2 RT. The only variable in there is temperature. Temperature wasn't changed, so the correct answer is C. The average kinetic energy stays the same. There's no effect on the kinetic energy, even though they're in a larger space. Next question is number 11. Number 11 here. So when 200 mils of a 2.0 molar NaOH solution is added to 500 mils of a 1 molar hydrochloric acid solution, the pH of the resulting mixture is closest to, I'm going to go ahead and switch over to the document camera. Okay. So basically what you have is you've got 200 mils of 2 molar NaOH, and you've got 500, lot more mils of 1 molar HCl, and they're mixed together, and they want to know what's the pH most likely going to be. And so to calculate that, we have to figure out, well, how much of one of the other ions, or not ions, acids or bases are present, because NaOH and HCl are going to neutralize each other, but how much of the other is going to be left over? So how many moles of the sodium hydroxide do we have left? Well, we have 200 mils of it at 2 molar concentration, so 0.2 times 2 is equal to 0.4 moles of the sodium hydroxide, the OH hydroxide. How many moles of the acid do we have? 0.5 times 1, 500 mils times 1 molar, it gives us 0.5 moles of H+. So we have 0.1 moles in excess of H+ left over from the HCl. Now, what is the concentration? To find the pH, we have to know the concentration of the H+. So 0.1 over 0.7. 0.7 is now the volume of our solution, since we added 200 mils to 500 mils. And this is, you got to do some estimation here. You can't do it. You can't do it without a calculator. So 0.1 over, let's just say 0.7 is 1. So 0.1 over 1 is about 0.1 molar. So what is the pH? Well, the negative log of 0.1 is 1. That's just something you kind of have to remember. So like 0.0001, you're going to have to remember that's going to be 3. So whatever the exponent here is going to be, 0.1 times 10 to the negative, or 10 to the 1 here, that's going to be 1. And so you got to use that kind of logic to calculate what the pH is going to be, just off your head, essentially. All right, number 12 was the next question. It says, the table above shows the first ionization energy and atomic radius of several elements. Which of the following best helps to explain the deviation of the first ionization energy of oxygen from the overall trend? So if you look at this, remember, ionization energy is the amount of energy required to pull an electron off. We go 800, almost 1100, 1400, and then suddenly we go down to 1300. And they're asking us, what is the answer? Why is that happening? Why are we going down in ionization energy? The answer to this question we went over in our periodic trends unit. Remember that we have the Aufbau diagram, and for boron we have P1, for carbon we have P2, for nitrogen we have P3. Remember that for the p orbitals there are 3 of them. There are 3 p orbitals in that sublevel. When we add another electron to the p sublevel with oxygen, now we have 4 electrons in the p sublevel, and one of those orbitals is now has a paired electron, and those electrons are repulsive to each other. So in essence, it's energistically favorable for the atom to actually remove that now paired up electron. So the correct answer is C. There is repulsion between paired electrons in oxygen's 2p orbitals. That electron that's now paired doesn't want to be paired. Remember, Hund's rule tells us electrons would rather not be paired. They'd rather be in their own spaces. So C is the correct answer. Next question is number 13. Whoops. Which of the following equations represents a reaction for which the standard entropy change is positive? Bring that all up there. So we're looking for a reaction here, A, B, C, or D, that actually is going to increase either the number of moles of product from the reactant side, or we're going to have a shift from a solid to a liquid, or a solid to a gas. So we're going to move from a solid or a liquid to a gas, we're going to go to a higher entropic system. So A is not correct because we've got 3 moles of O2 that are gaseous, and we're making 2 moles of O3 that are gaseous. So we're actually decreasing the number of gas moles. That doesn't work. B, we're going from 2 gases to 1 liquid. Oh, I need to pause for just a second, guys. Sorry. Okay. We're back at it. My little girl's over there doing her thing, playing. She was outside for a minute. It's very windy, though. Anyway, number 13 here. So again, we are looking at which of these reactions is going to produce more entropy. B is not correct because we're going from 2 gases to a liquid, so that's not correct. C is possible. I haven't looked at D yet. So we've got a solid, and we're going from a solid to another solid and another gas and a gas. So that one is probably right. And then D, we're going from a gas and a solid to a solid. So D is not correct. 100%, it's got to be C. We're going from a solid to a solid and a gas. Remember, gases have a lot more entropy to them. Next question is number 17. Well, this one. The potential energy as a function of internuclear distance for 3 diatomic molecules X2, Y2, and Z2 is shown in the graph above. Based on the data in the graph, which of the following correctly identifies the diatomic molecules X2, Y2, and Z2? This question is kind of weird because you're supposed to try to figure out which of these molecules it is based on where they are positioned on the graph. Now this graph is a graph indicating how much energy is involved in forming a covalent bond. So if you look over on this side of the graph, they're looking at diatomic molecules. I'm going to pause. Okay, back at it. Okay. So X2, Y2, and Z2. Which of these is H2, N2, or O2? If you look at this graph here, it's on the x-axis is the distance between the 2 atoms that are formed in the covalent bond, and then on the y-axis is how much energy is involved in that covalent bond. So X2, Y2, and Z2. X2. Let's look at X2 first. So what they're saying is that the molecules, the atoms are pretty dang close to each other, but they have a very large amount of energy to be close together like that. So basically they're overlapping, and we've got those electrons and protons repelling each other. And as we pull the atoms apart, there's going to be a point at which that covalent bond forms, and we have the lowest possible energy. And that's where these dips are right here. All right. How do you figure out which of these is H2, N2, and O2? This is based on the size of the atoms. So X2 has got to be X2 has got to be H2 hydrogen because this is the shortest distance between the 2 atoms, but it's at the same energy. So notice they all start at the same energy, and that's when the atoms are the closest to each other. So H2 is going to be able to be closest to each other. The atoms of hydrogen are going to be closest to each other because the hydrogen is the smallest possible atom. And then Y2 would be the next biggest, and that would be nitrogen, and Z2 would be oxygen because that would be the next biggest. Nitrogen's smaller than oxygen. Oxygen's the biggest. Okay, next one is number 28. Okay, so we got a reaction here. We have a rate law. A reaction and its experimentally determined rate law are represented above. A chemist proposes 2 different possible mechanisms for the reaction, which are given below. Based on the information above, which of the following is true? So we have to figure out which of these mechanisms is correct for the rate law. Remember that for kinetics, the rate law is based off of the slow step. So the slow step here, my daughter wants the bubble machine on. The slow step here would be the rate determining step, the RDS. So the rate is equal to K times X2. So mechanism 1 has that as a rate law, because remember the rate law is based off of the reactants. So X2, there's just 1 mole of X2, and that would go into the rate law right here. And then it's the same for mechanism 2 over here. They have the exact same slow step. So we're really looking for the answer where that says that both mechanism 1 and mechanism 2 are consistent with the rate law. So the slow step fits with the rate law given here. And so that's C. The answer is C. Number 30. Is this one it? There we go. All right. This is an interesting question. It has to do with hydrogen bonding. Thymine and adenine form a base pair in the DNA molecule. So DNA is double helix, and then the two base pairs, they link together based on hydrogen bonding. So they form a connection via hydrogen bonding. Which of the following diagrams shows the correct representation of the hydrogen bonding, denoted by the dashed lines between thymine and adenine base pairs? So we are looking for hydrogen bound to nitrogen and oxygen correctly in this picture here. And so what is the correct answer? Number 30, the correct answer is D. I'm looking at this one here. Number 30 is kind of a weird question because D is correct because hydrogen and nitrogen and oxygen are correctly set up here. Remember, hydrogen bonding is where you have hydrogen bound to either oxygen or nitrogen or fluorine. And that's just an intermolecular force. A shows it correctly. Hydrogen to nitrogen here, hydrogen to oxygen here. B isn't correct because oxygen to nitrogen, that's not hydrogen bonding. And C, that's not hydrogen, it's not hydrogen to hydrogen. But D is exactly the same. I am not sure why A isn't correct. So if you thought A, I think A makes sense too. And it seems like some kind of typo or something there. But A and D are both correct. Remember, hydrogen bonding is with hydrogen bound to oxygen, fluorine, or nitrogen, the very most electronegative elements. So that's kind of a weird one. I'm not sure why they marked D correct, but not A. Weird. Okay, number 32 is the next question. Okay. So we've got this reaction here. It says in a titration experiment, H2O2 reacts with aqueous permanganate as represented by the equation below. The dark purple KMnO4 solution is added from a burette to a colorless acidified solution of hydrogen peroxide in an Erlenmeyer flask. Note that the solution is pale pink at the end point. Number 32, at a certain time during the titration, the rate of appearance of O2 was 1 times 10 to the negative third moles per liter second. What was the rate of disappearance of permanganate at the same time? So let me bring up the document camera to answer this one. So they tell us that the rate of appearance of oxygen is 1 times 10 to the negative third moles per liter second. They want to know the disappearance. The answer to this question is just using the molar ratio between the oxygen and the permanganate ion. So it's a 5 to 2 ratio, and so we're going to take that 1 times 10 to the negative third moles of O2 and multiply by the molar ratio, which is going to give us 2/5. 2/5 times 10 to the negative third. I'm just kind of setting this up because we don't have a calculator here. So what is 2/5? 2/5 is 0.4. Multiply 2 and 5 by 2, and you get 4 over 10. So it's 0.4 times 10 to the negative third. You could write that as 4 times 10 to the negative fourth. 4 times 10 to the negative fourth, and that is going to be the answer, which is D. Okay. Next one is 33. Which element is being oxidized during the titration, and what is the element's change in oxidation number? All right, so we're looking at this reaction equation up here, and we have to figure out, well, which element is being oxidized, and what is the oxidation change? This is always going to be true. If there's oxygen involved, oxygen is going to be oxidized. Always. No ifs, ands, or buts. Oxygen is always oxidized. I'm going to put that up on the screen. Okay? Now, there's probably some exception to that rule somewhere, but oxygen is always oxidized. That's the whole idea. Oxygen is really good at being oxidized. And so we can look here at where the oxygen, what element is being oxidized here. And you can see that in the permanganate, oxygen is going from a -4 to a 0 from the left to right. And then in the hydrogen peroxide molecule, it's going from -1. I know that's crazy. Hydrogen's always +1 though, and hydrogen always wins on that one. Hydrogen's +1, oxygen's -1 in this case, and then we're going to a 0 on the O2 side, on the product side. So in both cases, we're going from -2 to 0 or -1 to 0. So it's being oxidized. Oxidation number is going up. And so we just have to figure out which of them actually gives us the correct answer here. And you can see here that it is A. Yeah. So oxygen, which changes from -1 to 0. It also goes from -2 to 0, but it's not on there. So -1 to 0. Okay, number 38 is our next one. So this is an acid-base one, but it's not going to be on the test, so that's okay. So data collected during the titration of a 20 ml sample of a 0.1 molar solution of a monoprotic acid with a solution of sodium hydroxide of unknown concentration are plotted in the graph below. Based on the data, which of the following are the approximate pKa of the acid and the molar concentration of the sodium hydroxide? All right, this is a question where you look at it and go, oh my gosh, I don't know anything. Yes, you do. Remember with the titration curve, the pKa of the acid is the pH at the half equivalence point. What's the half equivalence point? The half equivalence point is where we have used half of the necessary titrant to reach the equivalence point. Remember, the equivalence point is going to be this point on the graph. So right here, where we switch from acid to base, right in the middle. So that's where 20 mils of our sodium hydroxide are added, so the half equivalence point is 10. Okay? And so the pKa of our acid is going to be just a little bit under 5. So that's going to be either A or B. 4.7 is the answer for the pKa. Now, what is the approximate concentration of the sodium hydroxide? Well, sodium hydroxide and HCl, it's a monoprotic solution, monoprotic acid. So it's 0.1 molar monoprotic acid, and it takes 20 mils of NaOH to titrate it. We had 20 mils of the acid as well. Same volume of acid and sodium hydroxide are needed to be titrated. They're going to be the same concentration. So 0.1 molar is going to be the concentration. So same volume is needed to reach the equivalence point. So that means the same concentration is going to be needed. So the answer is going to be B. Number 39 is our next one. Okay, so we're looking at this heating curve here. And it says, how much energy is required to melt 64 grams of methane at 90 Kelvin? The molar mass of methane is 16 grams per mole. So melting, remember melting is where we use the heat of fusion. Remember that when you melt something, you're getting it from its solid phase, so it's being locked together in a crystal structure, and then melting it means you're breaking the intermolecular forces just enough so they slide past each other as a liquid. The amount of energy required to do that is shown in this part, Q, segment Q, and they give us the heat of fusion. Remember that heat of fusion is the energy per mole required to break that intermolecular attraction. So how much energy is required to melt 64 grams of methane at 90 Kelvin? Let's do the math for that one. It's not bad. Okay. So they tell us it's 0.94 kilojoules per mole, and they tell us 64 grams of methane needs to be melted. Okay, so how many moles is that? Because the heat required is going to be heat of fusion times the number of moles. And so 64 divided by 16, that's 4. So it's going to be 0.94 times 4 estimate. It's going to be something a little bit less than 4. So something around 4, but less than. And so if we look at our test, that's going to be 3.8 kilojoules. And that's B. Next question is 46 that you guys asked about. Getting close to the end here. Okay, so they're asking about this this whole graph here with potential energy and stuff like that. But number 46 here says the reaction is thermodynamically favorable under standard conditions at 298 Kelvin. Therefore, the value of delta S for the reaction must be. So if a reaction is thermodynamically favorable, remember that means that delta G is negative. It's less than 0. So if a reaction is delta G is less than 0, we need to figure out, well, at what conditions is delta H going to be? So we can do our math there as well. Let's just set up our equation here. So our equation from the past that we should have memorized, delta G equals delta H minus T times delta S. Let's set it up as an inequality. So in order for this to have a thermodynamically favorable reaction, a spontaneous reaction, delta G is going to be less than 0. So then let's just do the algebra to figure out, well, at what conditions is delta S, how is it going to be bigger, how is it going to be different to delta H? Give me a second here. Okay, sorry. It's just a crazy place over here. So the question was, at what conditions or what delta H value is the entropy going to be? Let me just go back to the question here. So let's look at it together. Okay, so the value of delta S for the reaction must be, for this to be thermodynamically favorable at 298 Kelvin, delta S must be what? Okay, and so if you do the math, if you set up the equation and then solve for delta S in the inequality, you'll find that in order for delta G to be less than 0, well, delta S is going to be, it's going to need to be larger than this value over here, delta H over T, in order for delta G to be less than 0. So that's the answer, C. All right, number 47 is the next one. Come on, move down. Number 47 is kind of goofy. So it says, which of the following diagrams best illustrates how a displacement in an ionic crystal results in cleavage and brittleness? So cleavage and brittleness, cleavage is where you cut something. You break it in such a way that you cause a crack through it. And brittleness is going to be where the ionic crystal is sort of kind of breaking, or like the connection between the ions is starting to kind of to stagger, and they're not going to be connected as much. When I look at the pictures here, A is the correct answer. You can see that really, really quickly. So a displacement means like hitting it with a hammer or something like that. So if you have cleavage or brittleness, A is where you see that, where you have a break in the ionic lattice. B is not correct because what you're seeing here is you are seeing a displacement of the charge. So you see that this positive ion is shifting in place to give another charge to this guy over here. That's called ion displacement. That's not the same as cleavage or brittleness. C is sort of like, it's called a sea of electrons that you can look at there. You basically have a metal. It's positive ions, and then electrons are flowing around it. And then this kind of just shows that they're moving around. That's about it. D is more of a covalent bond thing. And what I would call this is called kinks. Kinks in the covalent bonding, where you kind of have some of the bonds sort of twist around and shift in place. Usually you see this kind of thing, this sort of behavior in a membrane. Nothing else really. So A is the best answer, cleavage and brittle. So these are probably just terms that we didn't get a chance to go over in class. I did have a slide on this particular topic, but I didn't get a chance to, obviously. So cleavage and brittleness. One other thing one other very small topic that I didn't get a chance to teach was alloys. So do take a look at alloys. Like what does it mean to be an alloy? Essentially, it just means you're mixing metals, two metals together. But there's two different types of alloys. You have, I can't remember their names off the top of my head, but there's two types where basically there's space in between and then a metal fits in there. And then you can have also a type where the metal is actually removed and you put a new one inside inside that spot. So those two types of alloys you should learn about. Off the top of my head, I cannot remember their names. That just kind of came to me while I was making this video here. But alloys is a good topic to remember as well. This is just the multiple choice from last week. I wanted to go over that for you guys just so you have the idea of how to do that. If you have any other questions, let me know. This was kind of a weird, befuddling making of a video. We're doing our best. So if you have any questions, let me know. Have an excellent day. See you guys.